Li giving us a talk. He doesn't really need an introduction, but he was in Taiwan for several months prior to this, in the Institute for Astronomy and Astrophysics as their director. So we thought it would be a good idea while he's here in Toronto to have him give us a talk. So go ahead.
Again, since every place has a different policy, in Taiwan, the policy is that speakers should not wear masks and everybody else has to wear a mask everywhere, including on the street. So if people would like me to wear a mask or not, let me know. I mean, fallback with a mask is it's harder to hear. Any preferences? There's no audio. Oh, I see. So mine is not blinking. Maybe that's the problem. Let me see. Let me just swap one because not blinking what it means is not.
Oh, well, somebody else says now.
We can hear you just fine.
Okay, not blinking. Now it should work. Okay, so I'm happy to give some of my latest thoughts on some mostly theoretical developments we've had on fast radio burst propagation. So Dylan and Job have been the main collaborators, helping us understand how to think about wave optics. What my theme is. It may sound like a very old topic, and it does go back a long ways, but things do change over the centuries of this particular problem that I found fascinating. So just to go through why it's of renewed interest. Many of you have heard of fast radio bursts. These are these short, bright events that go off many times a day that are unique, and that they are radio waves that undergo a phenomenon of strong scintillation. I'll explain that in just a second. But what that makes them unique in for any source, any distant source, there's some nearby sources. We don't have a laser pointer, do we? This is not a laser pointer. Oh, well, okay, no laser pointer. Otherwise, I could have done a real life demonstration of what a coherent light source is, like a laser. Can't do that now. But the point is that it creates interference pattern, just like LIGO. For LIGO, we know that it's got a Nobel Prize, gravitational wave, and that's because it can measure strains or fractional distance changes of a part in 10 to the 23. That's a small number. If you dial the same number in for fast radio bursts, you measure time delays of nanoseconds along different propagation paths, and I'll show you that in a second. Over distances propagating gigaparsecs, if you divide that, you get about 10 to the minus 26. So fast radio bursts are detectors that could be 1,000 times more sensitive than LIGO. So here is something special about them, and there's no other source of anything in the universe that comes anywhere close to such a dimensionless ratio. So that's time to think about what could this be good for and what can you learn. And so I'm going to recap a bit about what we know, what we think we understand, and how to use some of that information. Here, this is slowly getting aged. This is actually one of the earlier papers on fast radio bursts, the first Nature paper on this topic by Keel, Xian, who is in town but ill today, and others that we reported. This is the first that I'm aware of, the first published report that claims to have seen this phenomenon of scintillation, interference of fast radio bursts. So it says in the caption of this figure, the inset shows fluctuation in brightness caused by scintillation. So just an instant recap of what fast radio bursts are. They are these events that this projector doesn't show the whole story. Well, that the fast radio burst starts early at high frequencies, and the lower frequencies arrive delayed by lambda squared. You get a parabola in this intensity time waterfall, and that is given by the cold plasma dispersion relation. So you know that there's a lot of electron column between you and this radio source. This has been, at that point, there had been a few reports of fast radio bursts. But this is the first where we purported this phenomenon of scintillation, that some frequencies it's bright, some it's faint, and other frequencies it's bright again. And this is interpreted as the interference of multiple images of this fast radio burst, where this lensing for multiple images is thought to occur due to plasma in our own galaxy. It's like twinkling of stars in the atmosphere, which also causes scintillation. And that this relatively narrow frequency separation over which it goes in and out of interference. So in this case, we can calculate the correlation length is something like 1 megahertz is the width over which you get multipath propagation. 1 megahertz is about a microsecond time delay. And at a gigahertz, roughly, you can see that this is delayed by 1,000 wavelengths in order to get such an interference pattern. So here we have the observational measurement evidence that something is, that space-time is well-behaved, well-behaved or not, is doing something, you're probing something about space-time at a path in 10 to the minus 26 change along two different lengths of path. So these two lengths of path, different lengths by that kind of amount to give this interference pattern. If they differ by much more than that, then this width would be much, much more narrow. So this tells you that space-time is reasonably well behaved. That there was no other measurement of such behavior of space-time before this. So let's jump ahead a bit and waves. So yes, light is a wave. That's radio waves are waves. That's not a new concept. But we're used to, just to go back a little bit about the whole, what we learn in, I think, probably first mentioned in high school physics and then more so in undergraduate physics, the concept of describing something by either a particle or a wave. And what do we mean by that? And we have, our textbooks are full of these dual descriptions of things. And let's just go and review and have a new way of thinking about an old story. So remember, light can also, to some degree, be described as a particle. Photons are very much particles that go in straight lines or at least go on classical trajectories, some geodesic, straight or otherwise. So the short wavelength limit has generally what we call a classical particle interpretation. And I'm going to call this this trajectory, this classical trajectory along which a wave propagates, the Eikonal interpretation of wave propagation. Okay, so that picture is geometric. The wave moves along some path, but it remains a wave moving along that path, such that two different paths can still interfere, even though the light is, or the wave is following a geometric path. We don't have to worry about the fact that it's exploring all possible paths, which in some sense it is. I'm going to go back and close this loop that in a Picard-Lefschetz interpretation, that's the opposite. So for example, another limit where this is not as obvious is when you speak. Sound waves have wavelengths of about a meter. So you're a few meters, you're a few wavelengths, the whole room is a few wavelengths across. So it's probably not a good description to think of these sound waves as being particles that bounce off anything and come back at you again. It's going everywhere all the time. Okay, you've got to do a full path integral to figure out which corner is a dead corner and which corner has resonances and other complicated things. So sound propagation is, again, a wave propagation, but in the long wavelength limit. And there, usually we just say, oh, it's complicated. You can do yourself a three-dimensional calculation. And I know some people like Jose use this expensive software called HFSS, it is called, that you pay a lot of money for to calculate these wave propagations and figure out what happens when a wave hits an obstacle. That's what that software does. And so that's considered to be a hard problem, and you just have to simulate it on a big computer for even a small problem. So I think the sound in this room is kind of a problem that will take a big computer to compute for a long time. And it's not particularly insightful. You get some answer, and the black box in, black box out. Hard to get a lot of intuition on this. In Picard-Lefschetz, I'll try a little bit explaining how that is an alternative interpretation where all these complicated wave propagations can be thought of actually as discrete paths if you allow for the classical path to move in imaginary space. Okay, so if you only allow for real space propagation, then that's an incomplete description of wave optics. But if you now allow a classical path going through imaginary positions, mathematically, those two statements are the same, then you get an answer without having to invoke the existence of waves, except for the Eikonal picture. And that's a different way of thinking about it, that, oh, all this wave optics means that there is a different alternative way of describing all of wave integrals, including all of quantum mechanics, that doesn't require you to do this infinite dimensional path. So that's been used intriguingly for quantum cosmology, for quantum gravity, where it isn't quite clear what you mean by, where all the old tricks don't work so well. However, this Picard-Lefschetz gives you a direct mapping, and you can go back to classical mechanics and just say, oh, I'm just going to allow time to be imagined. You can just allow trajectories that previously are not taken so seriously. Yes. And since we're back at basics here, to remind ourselves how one can get what some of these analogies takes, we often teach that light takes the shortest path, which is not actually all that useful a statement. It takes an extremal path. It can be the longest in some cases, subject to this. When you do a variation and you find that any stationary point, which is an extremal, can be a maximum, a minimum, is a classical solution to the wave equation. This again has been a one for a while. I think it's often called Huygen's principle. It must have been 400 years old now. Did anyone remember their history? I'm looking at a Dutchman here, so who might remember his history better than I do. That this is not a real new concept, that you have waves propagating, and something like that often, in some sense, describes everything. In some sense, describes nothing. To say, oh, a wave goes somewhere, at every point you spawn an infinite number of new waves, and every new wave spawns infinitely more new waves, and then you're done. Good luck. This is a nice way of saying it, that in practice that may not actually help you calculate anything. Just says, oh, it almost seems like therefore you know nothing. So then let's go into things that the two extreme limits. The things that kind of merge these concepts are path integrals, where you actually quantify that. I actually let Feynman or Kirchhoff path integrals just say, let's do this integral, and we'll get to that in a second, and just see what we can do with those integrals and how intractable they actually are. And here's an example from Wikipedia of how you can calculate Snell's law, the angle of bending between two media of propagation of any object. In this case, I think they probably had light. I think it is, oh yeah, it says air and water for light. We just said that. I'm just going to jump ahead. A lensing setup. So let's try to start off with a problem that we're going to try to compute something with. You have an object in a source plane. You have some perturbation to your propagation in a lens plane, some lens. So it could be my eyeglasses. I need these because I don't. Some of you do, some of you don't need these things. So once they do, probably have a much more close to your face feeling about what this does to light. And then there is a observer plane where the light at the end gets measured. And then the exercise is to calculate how the light will actually propagate. So in this problem, it's really only a 2D problem because we only have one plane, where we only allow for one plane that is a non-vacuum propagation where something interesting happens, meaning I've got a lensing potential which describes the delay, the extra delay, could be negative, imposed on this distance. Okay, so that's some phase delay that's induced in here. Some function can describe. In the case of glasses, it's the thickness of the lens as a function of position across the lens. And you write this out. Here's the equation you're supposed to solve to figure out what's going on. There is an integral, that's called the Kirchhoff integral, also a path integral. The language used is sometimes a bit different between wave optics and quantum mechanics, but it's actually the same integral, that a particle also takes all possible paths. In the case of a particle, this object is called an action. We use the variable s. So since Kirchhoff integral does the same thing, I'm going to use the path integral letters. S is an action. In this case, the action is, first of all, integrate e to the I s theta over all possible paths theta, that is all possible paths in the lens plane. And there's a geometric delay, which is the deflection you've done in that lens plane. And then there is the intrinsic delay caused by the lens itself. I'm going to call it psi. So if you say, even if nothing happens, even if you have no lens at all, let's say set psi to 0, it might not be entirely obvious. If you give this exercise in first year calculus, I'm sure you can trip on what this integral would be. If you just integrate e to the I theta minus mu quantity squared d theta. Anybody good at doing quick integrals in your head? You can give it a try. It's actually, you might know that this is an oscillating function. You can, can expand e to the I theta as cosine theta plus I sine theta. You're going to integrate cosine theta squared from minus infinity to infinity. It's a function that keeps going up and down. Not entirely clear that this is a well-defined question, and it can get worse than that. But for those of you familiar, if you don't worry about the details, in your textbooks, it'll tell you, well, you have to take the variation, so the extremum, just remember what we said in Fermat principle, extremum of the action are points where the derivative of s relative to your coordinates is 0. And those solutions, they call it stationary phase because the phase is stationary, it's 0 at that point. And because you have something that highly oscillates in these regions, they don't oscillate so much, so they actually contribute something. That's kind of the heuristic statement. And if you want to spend some time, you can actually think about why that is. I'll give you an example of psi in the next slide. We'll get there in just 1 second. Right now, psi is 0. So let's just do the part when psi is 0 and just figure out what to do there. And of course, if psi is 0, you just get theta equal to mu as the solution. And that's not quite as hard. Now, there are 2 types of this geometric limit, and I'm going to try to use these words. They're not used consistently in textbooks, but I'm going to use the word geometric for the additional constraint that you only consider solutions where these theta, these solutions are real. In fact, whenever you get to there, usually these textbooks will say, oh, theta has to be real, otherwise ignore this thing. And you've lost something. You've not evaluated the whole integral. You've thrown away certain things. Well, you haven't evaluated integrals anyways, even if you only use stationary solutions. So obviously, you're going to see that this is going to be hinting at, well, there are these imaginary solutions as well. So where you consider what that would be saying. It's saying the light. I mean, my integral is only done over real theta, right? They might say this seems kind of like a stupid thing to do, to consider a theta that I didn't actually integrate over. Why am I even wasting people's time to talk about integrating along a place where this integral wasn't meant to go? Well, that's where Picard-Lefschetz theory gives an interesting alternative way of doing this. Here is, I'm going to jump over this. This takes a long time to explain. I'm just going to show a few amusing examples of integrals and that was in 1D. 2D, so the problem we set up to do, the integral you're actually supposed to evaluate is integral of sine r squared r dr. Okay, that's the integral that we're supposed to do there with an I in front. Well, there's an I in front, but that's not important. You know, if you think about this one, I think in calculus class, if you wrote an answer other than ill-defined, you'll fail the test. So this is supposed to be an ill-defined integral because you can see every time r increases by 1 over r, the oscillation gets larger and larger. So you've got a bunch of numbers that get larger that you're supposed to add up, and that's going to diverge. So this is going to be problematic in our normal convention of calculus. Okay, there's a question of let's do some potentials, some more interesting potentials here. There is, by some metric, the simplest function that is, well, what do I mean by simple? This function, 1 over 1 plus theta squared, is simple in the sense that as theta gets large, this becomes 0. As theta goes to 0, this goes to a finite number, well defined, well behaved everywhere. It doesn't, this goes up and comes back down, a bit like a Gaussian. But because it's a rational function, you can actually take derivatives and solve the derivatives. By the way, sometimes you think of a Gaussian, perhaps e to the minus theta squared, you say might be an easier function for some. But if you try to differentiate it and set it to 0, you'll find that, well, this gets actually hard out very quickly. So this is a function for which it's a polynomial after you do this, and you can actually count how many roots you get. If you plug this in, it's the previous equation. Okay, you've got theta minus mu plus this quantity. You're going to differentiate it and set it to, well, this actually does this equal to theta. It gives you the other terms. The gradient for theta squared gives you theta. And when you solve this equation, this is a 5th order polynomial because 1 over theta squared differentiated gives you 1 over theta cubed. Actually, you get squared first. Anyways, homework exercise, you go through this. This is a 5th order polynomial. After you multiply all these things up to the numerator, has 5 complex roots. We've learned that somewhere, and I think I learned it in high school, that a 5th order polynomial always has 5 roots. Because it is asymptotically, it's differentiated once, it's an odd function. It has at least one real root, one real intersection, because it goes from minus infinity to infinity. And therefore it must cross the real line either once or 3 times. Okay, you might wonder, could it cross 5 times? That form it turns out cannot. So because the only number you can change is alpha. So no matter what value of alpha, you can get either 1 root or 3, or 1 real or 3 real roots. And I don't know what they teach nowadays. When I went to high school in Ontario, I think they did tell us, I think they did in high school, maybe this is all blending a bit, is that the other roots are complex. So it is not what by imaginary mean. If there's 1 real, there'll be 4 more complex roots. If there's 3 real, there'll be 2 more complex roots. So the total number of roots, real plus complex, is always 5. Okay, so that part is certain. Now, if you now integrate this up, we said, well, there can be, so we already know it, there can be 1 or 3 real stationary points, meaning you can have 1 or 3 images of this lensing system. So this thing can appear, well, unfortunately, these divergent lenses don't do this. But if somebody is, well, if one were farsighted enough, I need to custom order a lens somewhere that can demonstrate this on a tabletop. But anyways, you can get up to 3 images of a source behind you. And then there are these imaginary, these complex ones. I'm going to first give you the basic result of Picard-Lefschetz theory, that at most 1 of the imaginary images actually contributes to this integral. funny result, not obvious. It could be up to 4 imaginary images. Well, anyways, and that these imaginary images can actually be brighter than the real image. Okay, so first of all, we need a new vocabulary, that some of the imaginary images are real. That's a terrible word of English. That where some of the imaginary images are less real than others. I think we need, that's why this imaginary and real. We need to think a little bit. If anybody has good suggestions, I think Dylan will also be very thankful to anyone who can deconfuse the subject. So I'm going to draw a little bit about what this function looks like. This is the having taken the, no, this is before I take the gradient. This is just the action function. No, this is the gradient of the action function. This is the equation we're going to solve. So depending on where we set mu, you can either have one solution, one real solution, 3 real solutions for this equation. And you might want to say, well, there's exactly one point where you have an even number of solutions. So when we say that there's either 1 or 3, of course, there is a very singular point where these 2 solutions merge into one. The brightness of each image is the slope of this curve. So this particular point is peculiar in a number of ways, including that the brightness of this pair of images is infinite in the Eikonal limit, at least. Okay, so you get a pair of infinitely bright images, very special point. You get real images. Here, I've drawn a dotted line is where the real part of the imaginary image sits. Okay, and you can say, oh, but they're more real parts of imaginary images. They're not. There's only one imaginary. There's only one imaginary image that is real, that you will actually see an interference pattern of this image against, like these 2 images actually interfere, and the other ones don't.
Question?
Yes.
If the source has a finite size, then there's no well-defined way of saying when an image splits in 2, is there?
Well, I mean, well defined. So then you have to do an integral over the source plane. You're going to smear out the position it's actually at over, you decompose it as a bunch of sources that averages over what you see. So in that sense, it's ill-defined in the sense that you mix regions with with 3 images with other regions which only have 1. Computationally, it's straightforward. So I think in Dylan's simulations, he's well set up to just convolve this in the beta coordinate over some source function, and indeed, some of these oscillations can go away if you average over too much source size. However, on the left here, the imaginary images are far separated. So even if you smear it a bit, this could be quite robust to smearing. So it depends a bit where you are now. Obviously, they can still go away but that gets a bit technical. But indeed, these are for point sources, and FRBs are special because they don't smear. And that's why this has been not so important in any other astronomical source, because they do smear and you don't have to worry about this nearly as much. Okay, so here's going to be a 1-slide description of Picard-Lefschetz theory. Let's see, I think I have a second slide that actually describes this a bit more geometrically. So let's start with the middle description, which is when you're on axis and you're supposed to be doing an integral. So this is the theta axis you're supposed to integrate over. You were supposed to run an integral in this wave integral along the real axis of theta. The vertical coordinate is the imaginary part of theta that you were supposed to ignore in the original definition of this integral. Note, of course, integrating a complex function along the real line. Now, from elementary complex variables, we know that the value of the integrand is independent of the path you take as long as it does not cross any poles. So you're free to deform the path to a path that may be easier to evaluate. So in Picard-Lefschetz, and in this 1D case, that is similar to the method of steepest descent that's sometimes taught in asymptotic theory. What you do is you look at the real part of the integrand, and you deform your contour to minimize the real part of this integral. And because remember, we have these stationary points, they're saddle points, where the derivative is 0. So at saddle points, when you, what we call, flow down your contour to lower lying real values, then the contour will go up, and the saddle point a local maxima along the contour, and then it descends again. Here's a pole, the black point are poles. This is actually from a paper. And it goes from, it has a pole at infinity. So when you deform the whole thing and everything is said and done, the contour goes from minus infinity up to some saddle point, back down to the pole at minus infinity, back out again. And then you have the 3 images. And remember, in this integrand, the real part of the action is exponentially suppressed. So when you're very low, negative in real, it does not contribute to your integrand. So it is only points near the saddle points that matter. And also, once you do this rotation, and if you work through the details, you will find that the integrand is constant and not oscillatory. At least that the imaginary part is constant. The real part, along this contour, the real part is varying, and there's no oscillation, meaning you're integrating a real function. There's some subtle details about this slopes changing, but the basic concept here is that you've converted an oscillatory integrand into a non-oscillatory one. So you've converted a wildly oscillating function into a number. The integrand of a constant function is just a number. So each one of these lines, they're called thimbles, corresponds to a complex number. And this complex number can be associated either with a stationary point, which is called the Eikonal approximation, also used in asymptotic theory. In Picard-Lefschetz theory, you say, well, that's okay. Even if that approximation does not hold, of expanding as a curvature on that point, just do the full integral. It's just a number. It's a sum number, meaning that this whole infinite oscillatory function you can write as a sum of 3 numbers. Okay, so there's no more oscillation, and in classical mechanics, I would have called those 3 images or 3 trajectories, and that holds arbitrarily deep in the wave limit now, and it's exact. There's no approximation made. You will get the same answer. So this interpretation gives you the same answer. Let's try it over here. This is the impact regime where you only had 1 classical image. Remember, this polynomial can sometimes only has 1 root. You're doing this integral along here, and what it tells you is that if you solve this gradient equal to 0, you get only 1 root. There are 4 more, 1, 2, 3, 4 in the complex plane. I actually remember, I really think it was high school algebra, that these things come in complex conjugate pairs. That for every point underneath in the negative complex plane, there will be 1 up here. And then the statement we just made about there only being 1 real complex image is that when you do this descent flow, well, this real one we're already done with, here there's the final contour only passes through 1 complex saddle point. That's what I mean. There are 4 saddle points, and only 1 of them contributes to this integral. When you do the sum over thimbles, the Picard-Lefschetz sum, it is objectively true that there's only 1 complex image, and that the other points do nothing. They don't contribute anything to your integrand. Therefore, we have a 1-to-1 map, so you can describe all of this wave mechanics, and this is exact as a sum of images, but you have to allow for these images to be complex. And then you get the exact same numerical answer. by either doing this complicated wave integral Huygen's principle, every point adds to every other point, and good luck. Or you can just say, I have a real image, I have an imaginary image with a complex amplitude and phase. I add them up, and that's all you're going to see, and this statement is exact. Okay, it's not an approximation, it's a new interpretation, because you've written this oscillatory integral as a discrete sum over classical trajectories. Each stationary point, we said, is a classical trajectory. Mu is the position on the, so in this case, I'm fixing the potential to be a function of theta, and mu is where the source sits. So as the source moves, it moves from a region where there's only one image at very negative mu. So when the image is far away from the lens doesn't care about the imaginary route. And then as you get at some point close enough by, at some point you get an infinite lens. So when you're on axis, there's 3 images. And then if you go far enough away, the other side is back to 1 image. So mu is the position of your source at a distance. So here it is again. In the Picard-Lefschetz interpretation, the whole oscillatory integral is a sum over symbols. Each symbol is a one-to-one map to its maximum, which is a stationary point, and that's called the Eikonal value. And you can extend Eikonal value that when you're far away from geometric optics, the first order expansion may not be exact, but the fact that it is a real number, or a complex number rather, is still exact. Meaning that each symbol we can think of as an Eikonal interpretation. So this gives you a alternative interpretation of all path integrals, including all of quantum mechanics and quantum gravity. That all of quantum mechanics is encoded by a sum over what we already knew about all the real classical paths that already we learned in classical mechanics. This includes the imaginary ones. Yeah, that's all quantum mechanics can do to you. So it's not infinitely complicated, it just kind of doubles your degrees of freedom. I mean, roughly speaking, as you saw in this example, I mean, you can probably cook up an example where you have more complex roots than you have real ones. Even though you may think you have 4 complex roots, you really only have one that is a valid symbol. All the other ones don't actually matter. So a typical equation, you get some number of real solutions, some number of imaginary ones, and just figure out which ones actually matter. And this has been reinterpreted as a new description. I wouldn't call it a new derivation. You're doing the same integral, but it's a new, I would say, interpretation of a path integral, and therefore of quantum mechanics, by a number of people. These two came out almost at the same time. They didn't seem to know about each other, as often in physics, that independent people independently they come up with the same idea at the same time, and not 100 years early, not 100 years later. What's the chance of that, right? So this is nothing in here is all that new, and yet this, I guess, thoughts converge.
Question?
Yes.
Before you go on, so I as I understand it, there are sort of 3 regimes. You can imagine that the Fresnel scale is very small compared with the angular size of the lens. Then basically you have the Eikonal approximation working, no?
That's right.
Or you have the Fresnel scale comparable to the size of the lens, or it could be much larger. Now, my question is this Picard-Lefschetz formalism an exact description in the 3rd limit? Or, I mean, I have a difficulty imagining that it's actually exact description in the intermediate limit where the 2 scales are comparable. But am I being pessimistic about that?
Yes, you're pessimistic, and Dylan can walk you through all the combination that can happen when you might think this all should break down. And in fact, in the intermediate regime, I find actually in hindsight it's not that hard to see what's going on. You can decompose the interference pattern as these symbols. What I found more counterintuitive is deep in the wave limit, but the Fresnel scale is much bigger than anything, much bigger than any separation of your lenses.
Yes.
And there you can do a different expansion. There's a perturbative expansion, which actually gives you a different answer, different image counting. Everything is different in the diffractive limit. So there is a diffractive description deep in the wave limit. Where initially we thought surely they cannot both be true. I mean, surely you get the counting is different. This must all be nonsense. It turns out that that limit actually in the Picard-Lefschetz, if you actually compute the symbols, you get funny phenomena. You get the fact that sometimes two symbols are dominated by points where they are very close to each other, and they cancel almost perfectly, such that when you take that limit, that pair goes away, it doesn't contribute individually anymore. So in that limit, it turns out you fully recover the perturbative limit, the diffractive perturbative limit. Even though the Picard-Lefschetz is still formally exact if you allow for this pairing of canceling images.
And the last question is there any restriction here on the symmetries of the lens?
No restrictions. I mean, this happens to be symmetric. This doesn't change anything.
So you could have an arbitrary two-dimensional surface density profile or plasma column profile on the sky.
Okay, when you say arbitrary, I'm going to put the caveat in here that this is complex analysis, so they have to be analytic functions. And then you may say, well, if I measure something complicated happens. Well, like, our pictures, I can always expand any function as a per-day approximant into rational functions, and that converges very quickly normally for a smooth lens.
Or you say you have to express this angular profile as an analytic function.
That's right, because otherwise it's hard to continue this into complex planes. These imaginary trajectories require a function to have a meaning in the complex parameter.
Oh, okay, but just to be concrete, if I had some ordinary but not very symmetric galaxy, then in general I can only make a certain approximation to its surface density profile with an analytic function, I guess.
Well, again, I'd recommend per-day expansions, and those converge very rapidly. Those are rational function expansions that approximate just about anything.
Okay, thanks.
Yes. Do you encounter caustics for different size? Yes, you do. And of course, in wave optics, there is an infinite difference between an infinitely bright classical image and a finitely bright wave optics image. In fact, there was this picture that I just jumped over. Is meant to describe the different contributors that there are pictures where this Eikonal green where things do blow up. And this is fully described still. So Picard-Lefschetz still holds even when everything else breaks down. That's a nice thing about it. And this gets a bit technical. So I think it's in one of your papers that describes how the finite wave in Picard-Lefschetz generalizes the Eikonal singularity. Okay, so let's, after this long technical excursion, get back a little bit about FRBs and do they actually care about complex trajectories? There are a few qualitative things that do differ. So, for example, there has been a long history, meaning ever since I was a student 30 years ago, there's been this idea that with gravitational lenses, when you see multiple images, when you can measure a time delay because the source is varying, and you can measure some other things, you might be able to measure absolute distances, geometric distances. That's been the concept. Now, I think it was taken for granted for the next 30 years that if you don't see multiple images, then surely you'll measure no delay. You need a second image to have to even talk about there being a time delay. Now, with wave optics, we said, well, there are these imaginary images. And I'm just going to dangle here that it is meaningful to say that you measure a time delay to an imaginary image. So in fact, it is not a necessity that you form multiple real images to have time delays. Okay, qualitative change with wave optics over non-wave optics. It's only because, of course, it's only good for sources that exhibit interference phenomena like FRBs. And there's a bunch of papers that Dylan and others have written on this topic that clearly we've been very excited about all these new phenomena, all these new observables, all these new potentially precision measurements you can make, micro lensing, macro lensing. Maybe someday certain forms of gravitational waves. There's still work to be done. That's still an unfinished thing that we started off with. We were very ambitious and thought that surely that's the most interesting thing to compute first, and thought some things are harder to compute than others. So that's still an open question. With Olaf, we did do some of the gravitational lensing. So instead of measuring time delays to a few hours, that's been the state of the art in that field I mentioned. Let's imagine you can measure to microseconds or nanoseconds. Well, that gives you a different type of fidelity. Because the problem has been, normally you might think, oh, just measuring the time delay more accurately doesn't actually help you because you're limited by not knowing your lens structure, you're limited by not knowing the motion of lots of things you don't know. But the repeating FRB, as long as length is the same, then it turns out that because the universe is expanding, next time it goes off, it'll be more distant, and the time delay changes just because of that by many nanoseconds. And it's not just expanding. We think, at least some people think, it's accelerating. It turns out even that effect is large compared to these nanosecond time delays. Okay, so at least in principle, you're suddenly sensitive to things that before were just thought to be, no need to calculate, and suddenly there is a need to calculate and see what would actually happen. Lots of technical in there. I'm not gonna. Oh, I find the technical things. There's a paper out there. Stokes, I'm gonna jump over it. I don't think that's well, again, very technical. Dylan, I'm sure, will be happy to explain anyone who wants to learn about Stokes phenomena in these path integrals. That again, Witten has in his paper gives a beautiful analysis of it. Just recall that all of quantum mechanics, and that's going to sketch it out here, quantum gravity, you normally start off as a path integral and you try to do perturbation. Perturbation, what it really means is you do a Eikonal expansion around stationary points, which sometimes works, sometimes doesn't. In quantum gravity, people haven't quite figured out how to make that work properly. There are issues, divergences, other things when you go to higher loop orders. Higher order the perturbations, it looks all poorly controlled. And now that's why Turok and company, I thought, had a very nice systematic new interpretation that if you do this Picard-Lefschetz description, okay, and don't try to do it perturbatively, and as I just alluded to with Dylan, perturbative analyses can be tricky, and they can appear to be at odds with Picard-Lefschetz integrals. They're not actually, but the bridge between them can be very non-obvious, and quantum gravity may be one of these cases where this is tricky. So right now, I think the substantial progress has been made in mini superspace. So it's just quantum cosmology. So instead of trying to figure out everything at once, just ask what happens if the universe were to bounce or inflate. And again, I'm not going to go into details of it, but clearly this is a new tool that allows you to actually ask and solve this question without a lot of conceptual problems that we had before. And I think this just summarizes what I just said. So I think I've basically touched upon all the main topics that I wanted to describe. A few things to also mention, and there have been a few papers on this, is that wave optics, FRBs, I like them because there are a lot of them, thousands of measured FRBs. Similar physics applies to gravitational wave sources. So LIGO events are also coherent sources. So when they get lensed, you have to worry about wave optics in the integral because they're always coherent. They will always form an interference pattern. They're always point-like. for all practical propagations that we worry about here. And someday we'll have more of them, we'll have them further away. Right now, FRBs are much further away, have much better data, much brighter, much more signal to noise. So right now, FRBs are here, ready to go, ready to use. And in the future, gravitational waves share all the same qualitative behavior. So that's also an interesting topic to think about. Very different wavelengths. This is LIGO is like kilohertz range waves, whereas we're talking about gigahertz, so it's much longer wavelengths, different, much bigger Fresnel scale. With pulsars, you get nanohertz wavelengths, even longer. In the nanohertz, it turns out that Eikonal is never a good description for anything. So I mean, at least in the LIGO case, is an Eikonal. You can think of waves going on different paths and interfering. With nanohertz, that's never the case. You're always in the limit where your wave uncertainty is large compared to any smearing of any lens. So that's another interesting regime to think about propagation. Of course, there we have not had any definitive detection yet. Hopefully, soon to come. This is my last slide. That I've gotten sufficiently intrigued by fast radio bursts that one of the big new projects in Taiwan is to build a new fast radio burst telescope, where the goal is to have an array of feeds of telescopes that just watch the whole sky all the time. Okay, I mean CHIME, which holds by orders of magnitude the record of number of FRBs discovered, and does so by monitoring maybe 100 square degrees. But if 100 gives you so many events, I mean, the other ones might have monitored 1 square degree. Going from 1 to 100 is great. Why not go to 10,000? I mean, 10,000 square. There's plenty of sky. Well, plenty. There's roughly 10,000 degrees of sky overhead at any given instant, and there's 20,000 if you really go to the horizon. There are other practical issues if you go too close to the horizon. But let's say 10,000 is a kind of target to have in mind, and then you know exactly what to expect. You expect to see all the CHIME events, just 100 times more of them, because they can go off anywhere in the sky as opposed to having to go off where you happen to be looking. So that's a guaranteed way of getting more events, and the goal is to scale these up until you get well, the sky's the limit. You can get millions, billions of FRBs. There are lots of FRBs out there. And it's just a matter of us building instrumentation to search for it. And what I always thought is an opportunity is that so far all FRBs have been detected by telescopes built for a totally different purpose. So CHIME, and so I'm very proud that we designed CHIME the way we did with these cylinders. Of course, that was for the purpose of measuring 21 centimeter static emission. It turns out it's pretty good at detecting fast radio bursts. But of course, if your goal was to detect fast radio bursts, that's not what you would build. So you can do so much more better, of course, by optimizing a telescope, because you want the whole sky. I want every FRB that goes off. And what a question. You want outriggers to localize where the FRBs are. You want high resolution, high time resolution, high spatial resolution. You just want it all. And it's doable. So that's where there's a lot of discovery space. So if one wants to think about all the science one could do with FRBs, but you shouldn't just think about the few thousand FRBs that have been detected so far. You'd be thinking about, what would you do with millions or billions? Okay, so just to conclude all these things, I think I've said this a number of times now, that Picard-Lefschetz is the more every time we reread Huygen's paper, the more you kind of feel you get out of it, that this is really a picture that really gives you an alternative interpretation of optics, of quantum mechanics. That gives a new way of describing. It's not that new. Picard-Lefschetz theory has been around for 100 years, but at least it didn't really make it into physics until 2010. So in the physics world, it's really since 2010 that physicists, that's always like that. Mathematician language is often difficult for physics training to comprehend. Ed Witten, of course, is very special that he's actually more fluent in that language. So his paper is really a translation of past literature that gives us a new tool to think about. And that's where I think fast radio bursts are particularly promising. I mean, people ask me, why would you care about having even more FRBs? We have thousands, does having 1 million make any difference or not? Well, that's you to ask what are they good for? If your goal is to figure out where they are, or you might, having a lot of faint distant ones probably doesn't help you figure out what they are. But for wave optics and lensing, you do need them to be far away to have a bigger cross section to run into objects, to run through objects. So it depends, of course, on the question. And the real uniqueness of FRBs that I feel is very much underappreciated is that they're coherent. They form interference patterns. They give you this access to nanosecond timescales that no other source in the sky gives you. And there, we haven't even scratched the surface of the questions you can ask. And that's where I think FRBs and the future gravitational waves will hopefully let us get more access to our local universe. And again, this is not just FRBs, many other fields. So this, Witten, since this paper has really impacted a lot of physics. Thank you.
Well, if anybody has any questions now, feel free to ask. I think there was one question on the chat that I missed while we were, what situations will gravitational waves play a role? So I think, I forget when that was asked.
And of course, it's when you lens gravitational waves, and unlike electromagnetic waves, which can be lensed by both plasma and gravity, gravitational waves are lensed by only gravity. They act really with nothing but space-time. So you need when you have a lens gravitational wave image, so you need a source that's far away of a long wavelength for this to matter. These pulsar timing array supermassive black holes that there is a big effort out there that it looks like they're close to threshold of detecting them. Those will be detecting black holes near at a Hubble distance, so at the edge of the universe. For them, all this should always be relevant.
Question?
Yes.
So if one has a measurement of a lensing phenomenon, and it looks like wave effects are involved, how constrained is the inverse problem of trying to deduce the lensing potential from the data? I mean, the case of the point mass or it sounds constrained, but is it constrained in other cases?
So just to remind people of the geometric optics problem. So sometimes we observe objects that are multiply lensed, sometimes up to 4 or more. There may even be more. I don't know what the current record is of number of images you can see of a background object, galaxy or quasar. There is this inversion problem of trying to understand the lensing potential that leads to this lensing geometry. Sometimes you also have multiple objects getting lensed by the same lens, and then this is, it's a nonlinear problem. You've got to invert this. Sounds non-trivial. It's non-trivial. People have developed, again, 30 years. This is something that when I was a student was already a fashionable topic, and I understand it still is a fashionable topic. Some topics live for a long time, so good for student topics. If you can do this for 30 years, you're well set for employment. That with wave optics, you might worry that if the geometric problem seems hard, then the wave optics problems is if all you say, oh, now what you do is invert Huygen's principle, invert a path integral instead of just inverting the stationary points on it, you might think, I might as well go home. This is not even worth trying. That's where again I feel that this Picard-Lefschetz comes in. That now we can just think of this as a discrete collection of these real images plus a couple of imaginary ones. Now, surely that must be a nice constraint of how do you constrain potentials if you know what they're doing in the complex plane now. Okay, that's, I think you should take it as a positive exercise, and I think that's underexplored of how to exploit, mapping your potential not just along the real axis but along the imaginary axis. But the same tools, because I think many of the same tools presumably can be used, but just allowing them to take complex arguments.
Well, okay. So you're claiming that the lens is described by a discrete set of points, not actually curves. And if you choose those points, then the lens is completely described in full wave regime.
Yes, it's a two-step reduction, a reduction to a number of symbols, which are classical trajectories. And the symbol itself could be extended, right? It means even though it's described by a single integral that moves discretely as the source moves, it moves continuously and remains a single complex number which deforms slowly. Because the problem is wave integrals, everything changes rapidly. It's difficult to get any intuition on it. These symbols behave just like complex trajectories, that they move gradually as you move your source position and are well behaved in that sense. They can probe, of course, an extended region of your potential. So as your Fresnel scale gets large, then they're probing not just that point on your potential, but they're probing an average. And this average is a well-defined statement. So that's why this is a nice probe that it becomes not just a point probe, but a probe along that line in complex space. But only a line, not the whole thing, right? It only increases the complexity a little bit.
Okay, but it is essentially one-dimensional then, not point like the data you have to provide. You would have to provide in the inverse problem.
It's at least extended in that dimension, yes.
Yeah. Okay, thank you.
Any questions from the audience here? I actually have a question myself. So, you mentioned that the reason this wave optic stuff is being studied more now is because we have FRBs and gravitational waves, which sort of require it. But, before we've also had pulsars, and we've known that they exhibit these interference patterns for a long time. Scintillometry was observed, I don't know, a long time ago. So I wonder if you have a take on why it is only now that these wave optics ideas are being appreciated to a new extent, when there has been so much thought on wave optics. There was work being done previously on this in pulsars.
Indeed. So over the first, I'm going to say 40 years of pulsar scintillation, which is a class of objects in our own galaxies that were known to scintillate strongly, the interpretation had been that they are what's called fully diffractive, and in their vocabulary, diffractive means that you have a volume filling turbulence and all the bending angles are caused by eddies that are maybe a few hundred kilometers in size, and there are a very large number of these eddies between you and the pulsar. With that many degrees of freedom, you're not measuring nearly enough to figure out to reconstruct the density field. That's hopeless. It's just totally in the limit where you only observe, let's say, 1 million numbers or something in a scintillation pattern, in a pulsar scintillation pattern, but you have 10 to the 15 numbers that you don't know. So this is a highly under-constrained problem that at best can be described statistically. Now, over the last 20 years, since Dan Steinberg discovered inverted arclets, the evidence is that this is a misinterpretation of the data, that in fact pulsars are in the deep Eikonal limit, not in the deep diffractive limit, and that you're actually seeing interference of a modest number of images, which is small compared to the number of measurements you have. So now it looks like a number of our people in this scintillometry group have had good success in actually inverting. So this goes back to what Chris was asking. Can you actually invert? And before, I think the answer would have been no. This is hopeless. Don't even try. This comes from these tiny little structures, which you just cannot ever constrain. To saying no, it's only it's let's say 100 images. It's not tiny, But with a million numbers constraining 100 images may seem very tractable. And that's something which hasn't sunk in yet in the pulsar world. But I think the evidence is overwhelming. Not just, I mean, anybody I think nowadays who talks about turbulence is ignoring all the, I mean, I think people who work in interlopy are familiar with this phenomenon. But people I think are still have in their mind a 50-year-old picture.
Thanks. So are there any more questions? Is there a question here?
Imaginary positions, trajectories show up or are observed as multiple images. Well, both. So in a gravitational lens, for a wave source, there's in the Eikonal or the geometric limit, there are these caustics where you form infinitely bright images, and that suddenly appear, and you have a pair of very bright real images. On the other side of that caustic, you get a single imaginary image, and actually with a high resolution telescope, you could actually see that image at that location on the sky with enough resolution. For FRBs, this actually is conceivable because with VLBI, you could actually image your way into regions that are still imaginary and strongly lensed, and you will count, your counting will tell you there's only one image instead of two. So this odd image theorem breaks down because instead of having two real, one imaginary. So they can be arbitrarily convincingly observable if you're at the right place of the sky. Fangxi.
Yeah, so follow up. Do you mean we can actually see the imaginary, or are you just picturing the? Oh, do you mean see the imaginary, or are you just picturing the flux changes due to interference with the imaginary image?
You can actually see an imaginary image if you place the FRB at the right place in the lens. It'll be unambiguous. You make a VLBI image and you will say, oh, here's an image, here's a pulse, here's an echo of the pulse. And normally there could have been an even number of echoes. And now you'll see a single echo either in time or in space. And that echo can be much brighter than the original image. So I mean, it can be unambiguous that this is not, a small, tiny perturbative effect. It can be the dominant thing that you see.
Okay, so if there are no more questions, why don't we give another round of applause?